I'm going to talk about chords, okay? Chords are line segments inside circles with their endpoints on circles. For example, with respect to the circle I've just drawn, that blue line segment is a chord, okay? That second blue line segment is also a chord. So is that third line segment. That third line segment goes through the center of the circle. That's referred to as a diameter. So notice that a diameter is a chord. Now what I'm going to do is I'm going to prove various statements about chords. All right? So if I have congruent chords, all right, are the corresponding central angles also congruent? All right, I will claim that they are, but can you prove that fact? So here is what we're proving, or we're going to attempt to prove. Prove that congruent chords imply congruent corresponding central angles. All right? You may want to pause the video and see if you can prove this without my help. All right, so do that now if you like. So I'll go ahead and work this out. So let me draw a picture of a circle. Let me draw two chords, and we will assume that those two chords are congruent. And let me draw their corresponding central angles. All right, now we know that every radius of the circle is congruent. All of these radii have some length, and they're all the same length. So I can put the congruency markings. Okay, and then we can show that those two triangles, those two isosceles triangles, are congruent by using the SSS theorem, right? That says that if three pairs of corresponding sides are congruent, then the triangles are congruent, okay? Now, we also know that if we have congruent triangles, we know that congruent parts of congruent triangles are congruent. I sometimes refer to that as kyptic, okay? So that means that the central angles are congruent. So that completes our proof. So congruent chords do indeed imply congruent corresponding central angles. Okay? Now, does it work in the opposite direction? In other words, prove that congruent central angles have congruent corresponding chords. All right, so once again, if you like, pause the video and try to prove that without my help. All right, so I'll go ahead and do it. So let me draw a picture of a circle, and let me make two central angles. And I will assume that those central angles are congruent. I will further use the fact that every radii has the same length. Some length, we'll call it r. So I could put the congruency symbol on all the radii. And our goal, remember, is to show that the corresponding chords are congruent. Now, once again, I have two triangles, and I know that those two triangles are congruent from the SAS theorem. All right? And therefore, I know from the fact that congruent parts of congruent triangles are congruent, I know from the fact that that's true that the chords are congruent. All right, so that completes that proof. Now, let's do another one. All right. All right. Prove that if chords are congruent, then corresponding arcs are also congruent. All right, so pause the video if you like and try to prove that. All right, I'll go ahead and prove that now. So let's see, I need to make a picture of a circle with two chords that I will assume are two chords that I will assume are congruent. And let me also make a picture of the corresponding central angles. All right. Now, we know that the chords are congruent, or we're assuming that. And we further know, because we just proved it, that if two chords are congruent, then the corresponding central angles are congruent. Right? But we also know that when comparing arcs, you can compare their corresponding central angles. So because the central angles are congruent, we know that the arcs are congruent. Okay? So that completes that proof. Now, I'd like to do one more. All right, so this is your last chance to try to do a proof on your own without my help. So, if a diameter is perpendicular to a chord, it'll turn out that the diameter bisects the chord. Okay? So let's see if we can prove that. Prove that if a diameter is perpendicular to a chord, prove that if a diameter is perpendicular to a chord, that it bisects the chord. All right? So pause the video and try to do that now, if you like. All right, so let me go ahead and do it as well. So I'll draw a circle with a chord, and I'll draw a diameter, which is assumed to be perpendicular to the chord. So I will put a little right angle symbol, because we know that from the definition of perpendicular, that means that it forms, we have right angles formed. All right, so let's do this. Let's draw the radii with respect to the endpoints of the chord. And we know that all radii are the same length, r, whatever r is, so those are congruent. And notice that I have two right triangles with congruent hypotenuses that share a common side. All right, so I can use the hypotenuse leg theorem to establish that both right triangles are congruent. Remember that the HL theorem says that if two right triangles have congruent hypotenuses and a pair of legs that are also congruent, then we can establish that the right triangles are congruent. Okay? Now, you do have two sides, two pairs of sides, okay? But you can't use the SAS theorem because the congruent angle, the right angles are not in between the two sides with respect to the pairs of sides that you know are congruent, all right? And there's no such thing as an SSA theorem. So that's why we had to use the HL theorem. All right, so now we know that the right triangles are congruent, and by the fact that congruent parts of congruent triangles are congruent, we know that these sides are congruent. All right, so look at what we've just established. The two parts of the chord, okay, formed from the diameter are congruent. So the diameter divided the chord into two congruent pieces. All right. By the definition of bisection, that diameter is bisecting the chord. So that completes our proof.